Hi, Joan.
Hello.
Thank you so much for coming to Stanford
Thanks for inviting.
to participate in Stats 385, Theories of Deep Learning, question mark. As my first question, I would like to know about you and your background, and can you tell us a little bit about your journey to Courant?
Okay. Yeah, so I did my undergrad in Barcelona in a sort of technical, like polytechnical school there. At the time, I started to get interested in more like mathematical topics, but I did these double courses in pure math and electrical engineering. And then, I grew up. I kind of fell in love with my future wife, who is French, and so I had to move to France. And so this is where I went to École Normale Supérieure, where I enrolled in this master's program where they do applied math, machine learning, statistics. And there I spent, after some years, working on a startup with my future PhD advisor, Stéphane Malat. This is where I started to really focus more on, like, narrow down my interests in essentially, trying to apply some of the, let's say, methodology and tools that we as applied mathematicians like to, like really trying to understand things from signal processing, try to bring this philosophy to problems that involve, as we all know, nowadays machine learning and deep learning, etc. And so with that, I did my PhD there, and then after the PhD, I decided that I wanted to also experience research and life in the US, so I came to Courant as a postdoc first, and then from there I spent a very nice 1 year and a half getting acquainted and familiar with, I would say, how a traditional CS lab, or like Jan's CS lab, and trying to get exposed to other kind of ideas. And from there I was lucky to find a position at UC Berkeley in the stats department. I did the first also like a parenthesis in Facebook research, and then I guess that this brought me at the end to Courant as assistant professor in Courant, math, computer science, and data science.
Okay, great. You said data science, so I'm going to ask you about data science program that you guys have in Courant. If you can share with audience about the topics that is being studied in the data science program at Courant, or if you want to share with us any news from the data science program at Courant, that would be great.
Okay, so first, like a precision, the Center for Data Science at NYU is not at Courant, so it's really historically it's true that it grew and it started as an initiative from Gerard Venarose and Jan LeCun, who were both at Courant, but now it's really something that tries to be a bit more cross-disciplinary, tries to go not only like embracing, let's say, fundamental sciences like statistics and mathematics, but also going to the applied sciences. And so the topics that we develop there are, I mean, not because I want to sound cliche, but it's really the ideas that we want to really like try to interconnect and do our best to basically provide analytical tools and the way where we think about problems in maybe, let's say, applied math and statistics into different areas of the university where the NOU has been strong, like biology, political science, economy, etc. And there we have a physical space. We are bringing their people together where we can together figure out what is the best way forward to essentially train the generation of data, like students and researchers who are really comfortable going back and forth between applications and methods, between that they're able to find connections between different domains that can bring some benefit. And as the news or things that I can share, well, we have as I said, we have a PhD program in data science. It's one of the first in the country, and so I encourage everyone who is interested in figuring out, can help us to define what data science will be, to apply and to be part of this community.
Okay, great. So as my deep learning question, you have worked with Stéphane Malat on scattering networks, and and also you have work on convolutional neural networks. And there's some debate that these are very different. And I would like to know your opinion, if you want to summarize the fundamental differences between scattering networks and CNNs, what would they be?
Well, I mean, I guess that the main difference is that one is a signal processing tool that is defined as I would say as a classical tool in signal processing, where of course you have some parameters that determine, let's say, the properties of the wavelets, etc. But it's not a highly over-parameterized, and it's not as generically defined as a convolutional neural network, where a convolutional neural network requires some training data before it can be used and it can be defined and it can be understood. So I would say that on the one hand you have a tool that is built from its mathematical properties, and then you can apply it to data and you can reason about the properties of this representation to the data, whereas the convolutional neural network is it's defined itself through the data, right? Basically, you don't specify beforehand what are the properties that you impose into these filters, right? The properties emerge through the training process, and so
are scattering networks good for large-scale classification problems like ImageNet classification? So do you think there is hope that one can do classification using scattering networks on them?
I think it's going to be very hard to that any method that is not a convolutional neural network will be comparable in terms of performance. So in that respect, I would say that I would be very skeptical. I'm aware that there's a bet going on in the between Jan and Stefan of a very fancy dinner, that someday scattering will work as well as ConvNet in ImageNet. But I don't know what is the status of this bet. I don't want to comment. But what I can tell is that scattering, in a sense, they highlight one particular aspect of convolutional neural networks that relate to more like the signal processing properties of what the convolutional neural networks are doing, but it doesn't capture the problem, like the whole problem in its globality, right? That in particular it doesn't capture this property of convolutional neural networks to adapt and to specialize its weights in a very smart way to process large-scale data sets.
Joan, I wanted to ask you a question about Stefan Mallat. You have worked with him closely for 12 years. So can you tell us one thing that people wouldn't know about Stefan Mallat? Okay.
So I can tell you one thing that maybe someone here already knows, but maybe it's not vox populi, is that he's an incredible, awesome dancer. And he is a very, very good dancer of tango and salsa, and he made a very good impression in my wedding. So.
Wow. Okay. I didn't know that. Well, thanks. Vardan, you want to?
We sometimes do this association game with guest lecturers who come, where I tell you a certain phrase and you need to say a single word.
Okay.
Okay, so the first thing is CNN.
Fourier.
Scattering.
Wavelet.
Graph Laplacian.
Spectrum.
Stefan Mallat.
Tango.
Jan LeCun.
Jazz.
Theories of deep learning ?
Useful.
Thank you.
So, Joan, what do you think is the theoretical contribution that you can make to neural nets as practiced by practitioners? And to make this more definite, I'll envision a scenario. I think we could imagine that you're flying transatlantic and you happen to get an upgrade and you're sitting next to Jan LeCun for the flight over to Paris. So you have a chance to impress on him a theorist's point of view.
Mm-hmm.
what would that be?
That's a very interesting and profound question. So, first, I would not pretend that through my humble theoretical contribution to make his life any better or easier in the short term, right? I don't see myself as doing this tour de force where you just by pure theoretical reasoning you understand that you need to change something fundamental on the algorithm or the methods, and it automatically translates in improvements. I see myself more on the quest of figuring out what Jan has done and trying to separate the part of what he has done that is essential and is really like the seed and like the thing that concentrates the idea that really makes it work, from the part of what he has done that is maybe superfluous on that thing that that can be simplified or replaced. And so it's more like the work of just going after and cleaning up and maybe simplifying things. And so the contribution in that sense would be more for the posterity, no, not for the posterity, but for if one day we are teaching students about this a nice set of algorithms and techniques, what would we teach them? Are we going to teach them a bunch of architectures and a bunch of tricks to train them, or are we going to teach them something that is a bit more easier to grasp and easier to reason about, that maybe contains some theory, right? And so that's my humble point of view, but probably I'm not sure that would be enough to impress him. I don't know.
Okay, well, it's not necessarily to impress him. It's more to just communicate. So let's continue with this. So you decide you're next to him. Why not pick his brain?
Mm-hmm.
What would you try to get out of Jan LeCun? What kind of information could he reveal to you that you as a theorist would consider to be absolutely precious?
Okay. Yeah. For one thing, I have had the chance to work with Jan for some years, and I have to say that he is really someone who has a very profound geometric view of the problem. So it's not it might not be formalized mathematically, but he has this intuition where he can see and visualize problems very geometrically. So if I could pick his brain, I would be able to take a picture of how he sees let's say unsupervised learning, or how he what are his ideas, or what is his take on for example this elusive question of generalization, right? Whether he believes that this is a problem that will be solved using the techniques that we are currently developing, or if we are missing something else, right? And so I don't know, these are just a couple of things that come to mind, but maybe if I could think a little bit more, I would probably find many other examples where he can be helpful for us as theorists.
So the advantage of theory is in principle that it can penetrate mysteries. Is there something that you find mysterious about deep learning that you're currently working to penetrate?
Yes, I mean it's. I would say, I mean, if maybe I can start by answering by the end. So almost by definition, if I'm really working on understanding the theory of something, it has to be mysterious, right? Because a theory that is trying to understand something that is not mysterious, maybe, well, it's like the outcome is already expected, it's already there. So for me, the thing that I find, particularly mysterious about the current state of affairs is that, we don't understand. Basically, what we don't understand is really the generalization aspect of these models, right? So right now we are in this situation where there's all this like a number of elements that together create this this state where things work well. Okay, what does it mean that things work well? It means that our current theories that explain how a machine learning model should generalize, they are not there to explain the reality. And so to me right now it's just that we have these pieces that are starting to put that we can maybe try to attack them and study them separately, like the statistical side, the signal processing side, maybe the optimization side. But it seems that the mystery is that they need to be taken together before anything meaningful can come out of it. And so this is, I see it as a like a long-term quest, and I'm not expecting, at least myself, to crack this thing, in the short term. But it's like motivation to really continue to to put all these pieces together. Yes.
So you're teaching a course on deep learning from a theorist's point of view in the coming term at Courant.
Yes.
What would be an overarching theme of this?
So the overarching thing of the course, it's I would say, to maybe going back to your word, like to demystify, right? To really try to do this work that consists in trying to precise or to try to express some of the ideas and intuitions that float in the air. So try to move from open questions that people are wondering, why does this happen, why does this work, into precise statements or precise mathematical language that can be either proved or disproved, or that can be related to other areas of mathematics and statistics where people have a culture of really like talking this language, right? So I would say the overarching goal maybe would be to act as a translator, where you try to from the current situation of the field, try to identify phenomena and questions that are currently not well understood, and that are directly responsible for the empirical performance, or that are really that could have an impact on how we think and understand these models. Yes.
Thank you.
Yes, thank you.
My first question is, our course poster is a yellow submarine surrounded by creatures. I'm wondering, from a sort of psychological point of view, where people are trying to understand or characterize people by asking them where they're inside a certain room. Can I rephrase everything? One more. You know how in psychology you sometimes have people ask a person where he's inside a room. So for instance, I could tell you there is a table, there are many chairs, and there's a lamp, and I would ask you, from which point of view do you view the room? Is it from above, from the side, etc.? So I would like to use the same technique from psychology to our course poster. So where do you view yourself in the course poster? Are you inside the submarine? Are you one of the fish? Are you a sea creature? Or none of the above?
Yeah, it's an interesting question. So, okay, if the sea creatures correspond to, like pioneers and very, let's say, visible researchers in the field, I definitely don't see myself as one of these creatures, right? I might be maybe just a little, just a piece of sand in the bottom. Maybe, when there's current in the sea, this piece of sand is going to move, right? And so, trying to do my best to, maybe become like a plant, so I can have some roots and stop being so influenced by the current. But maybe also, I mean, from this perspective, I would be a bit jealous of the submarine, right? Because the submarine is warm, you are not cold, and you have maybe just tea to drink, and so in other words, just like a bit more seriously, I also feel comfortable, from this perspective of just someone who is, being in the submarine is someone who is just there as, trying to learn and to maybe, objectively, so someone who maybe belongs to another ocean, another sea, and is just taking, a trip to another community and seeing how this can connect to theirs. So, in other words, I mean, it's a situation that I would identify myself, right? This idea that you are never, the natural state of a researcher is someone who is always traveling, like intellectually, right? Visiting things that are kind of out of his comfort zone. Yeah.
So maybe you're like a wild fish or
Small
wild fish.
small piece of plankton. Yes.
Okay. The second question is, what is your current opinion about the current state of affairs of unsupervised learning, GAN, and the different approaches that we're taking over the years?
Okay. So so unsupervised learning is it's a very interesting word because it's like a placeholder for many things that we want to do, but we don't know exactly what they mean, or we don't understand exactly how to phrase them. And so it has historically meant the frontier, right? So everything that we don't know how to do but we want to do, this is unsupervised learning. So it's funny, the state of affairs now is as I say, as you could argue that it's dominated, at least in the deep learning community, by a small number of, let's say, techniques, the statistical techniques. One of it is the adversarial training, the generative adversarial networks. The other one is using ideas more from variational inference and basically a bit more Bayesian, I would say. So I don't know. It's an interesting stage because contrary to what one might believe, that it's like a fight, or it's like okay, let's see which theory is going to prevail. The way I see it is that now researchers are trying more and more to try to combine them, to combine the two strategies. And I'm curious to see how this thing is going to evolve, because the math, or like the model, the statistical model that are behind each of them are very different, right? In one case, you are still attached to the way of thinking in terms of likelihood, right? That you just want to you reason about things, about the likelihood of my observations under some probabilistic model. In the other case, it's now more and more this idea that maybe there's a different way to measure, the similarity between distributions, that is based more on, transportation measures and this class of techniques. So it's going to be interesting to see if this second trend is, at least in this scenario, gonna overcome, or is gonna become prevalent to the likelihood way of thinking about unsupervised learning. I don't know. I mean, it's certainly it's a question that for sure has happened before in statistics, right? That there's different ways where you can actually measure the quality of a model, and so I'm looking forward to see how this thing is going to evolve. I don't know. Yeah.
The next question is, so you have very different works in different topics. So you have your PhD work is about the scattering network. Then you have the work with applying CNNs on graphs, right? Basically, how do you apply CNNs that are built for Euclidean data to non-Euclidean data? You have the work explaining Lista, which is basically sparse coding oriented. You have currently the work of the loss. I'm wondering, what is the single connecting string to all of these beads?
Good question. Well, I would say that that I've been, of course, I've been deeply influenced by the time I spent with my advisor, and this notion that the signal processing really has something to offer to the field, right? And so at the end of the day, we are not trying to classify points in high-dimensional space. We are trying to classify things that have some geometry, that is something that can be studied and analyzed using tools that are that were developed by many people. David, one of the leading figures in this direction. And so I would say that this idea that you should not be afraid of introducing inductive biases, and you should not be ashamed of saying that, okay, my model is going to be analyzed, it's going to be useful that is going to work under these assumptions. I would say that this could be one connecting thread that in a sense contrasts with some of the more, let's say, classic theory in statistical learning theory that is very, let's say, I would say, is very universal, right? They attempt to say things that are going to apply for the broadest possible class of problems. So I would say that making this voyage from things that are very specific and heavily rely on the harmonic structure of the data, to maybe questions that become more and more universal. So yeah, and then I don't know exactly how this thing is going to evolve. It also depends on like conversations with colleagues, with students. I mean, yeah.
Another question is, if you had all the deep learning researchers on a single boat, and that boat was sinking like the Titanic, and you had a single life vest, this is the last question, so you can censor it. Who would you give it to? And that person will have to basically carry on the research of deep learning.
So, okay, so maybe I should think about like a.
You can cancel it.
I have to think about like either like someone who is very skeptical or someone. I don't know. I mean, it's true that it's very hard for me to pick. Like, I mean, I cannot objectively.
The boat is sinking.
The boat is sinking, so I have to decide fast. No, I don't know. Maybe I don't know. It's just that. I mean, just it's really like a personal thing, right? So right now, I'm really interested in. I'm curious on how, let's say, optimization is gonna save us, right? It's gonna really help us understand these things are going, and so maybe for reasons of proximity and history, someone who I think would be a good candidate for this saving, but not certainly the only one, would be, for example, Leon Boutou, who is someone who has been for many years doing a very, let's say, profound and pioneering work on really, and he gave us a lot of very important insight, and he's still currently very active and really creative and really original. But I mean, of course, many other people would, I don't want to say exchangeable, but I mean there are many people who would be equally deserving. But if I had to pick one,
let's assume you wondered about the boat and you found another life vest. Who are you giving the second life vest to?
I don't know. This is getting very hard. Do you want it?
I'm not on the boat.
Yeah. Okay. No.
It has to be pioneers of deep learning. He has his own submarine.
It's true. You're in the submarine. That's true.
We sunk the boat. It was our
okay.
torpedo. Yes. Yeah. No, I would say that certainly the objectively maybe the answer would be that it's. Not maybe more seriously. So it's true that the deep learning went through a period where you could count with your fingers how many people were actively working on that. I think that now we can safely say that that's not the case anymore. And maybe the life vest should go to this anonymous PhD student who is starting now, and who is really the one who is going to maybe help us understand what's going on. And now we can pick this student from. Very lots of different labs, not just in the U.S. I mean, Canada, as you know, very active, very prolific research labs there. In Europe, in CS departments, in math departments, in statistics departments. So now, I would say that the boat is, as you say, it's more like a Titanic, right? And so maybe just pick, do some kind of random assignment to and put some weights depending on the youth, and pick a a young, motivated researcher. And now we are lucky that it's gonna be, he's gonna save us.
Very nice answer. Thank you very much.
We're having Joan Bruna today from Courant Institute. Joan did his PhD with Stéphane Malat at in France, working on scattering networks. Then he came to America. He was an assistant professor in Berkeley before he joined Courant. He also worked at Facebook with Yann LeCun. And
Let's hear about topology and geometry of half-rectified network optimization from Joan. Please take it away.
Okay. Hello, everyone. Do you hear me well? Yeah? Okay. Well, so first, thanks to the organizers for such a nice and interesting initiative. And I'm hoping to spend more time after this lecture going through the other lectures and learning about the theories of deep learning. So, okay, so today I'm going to talk about some of the work that we did recently that kind of touches on, or at least like tries to scratch the surface of some of the mysteries or some of the things that might be, amenable to mathematical study. So the setup and the motivation that I will use starts, I'd say, like in a relatively standard machine learning setup, right? So what we are going to be studying first is this general class of problems, right? So you have a classical empirical risk minimization, where the goal of the game is to, you have a model that has some parameters theta. At this point, the model can be whatever. Then you have some data distribution, like a T, and you have some samples from this data, right, that correspond to this empirical measure. And so these are the two classical objects in machine learning. So you want to basically make this thing small, but the only thing that you can observe is this thing here, right? And so as my colleague Ben Recht tries to always says, is that there's this fundamental theorem of machine learning, right, that kind of states that basically the risk, the population risk that you are going to achieve with some model, you can you can decompose it as the training risk plus the generalization gap, right? And the theorem is just proven in the statement, right? And so but this in a sense sets the tone and basically divides, organizes this question in terms of like two different fields, right? So one is optimization, because you want to make this thing small, and the other one is statistics, right? Where you try to understand what is this generalization gap. And one of the things that we learn also from like a very nice and influential paper by Léon Boutou and Olivier Bousquet is that you should not think about this problem separately, right? I mean, basically the optimization that you use is in a sense, is an integral part of this question. And so, as we know, there's different ways where you can actually bound this thing and understand how the population is gonna deviate from the empirical laws. The question is one of the things that we observe is that now, if we want to bring these ideas to the real setup, where we have now the data is like images and labels, and the model is like a very wow. Okay, do you still see me? Okay. Okay, and the model is a large convolutional neural network. Then one might wonder, what is this? What is the validity, or what is basically how useful is the current control we have on this generalization gap? And so, at least empirically, one of the things that we observe as a field is that right now, if you want to be good at generalizing, there are essentially two ingredients that emerge as being at least the first order ingredients, right? That make things work in practice. So one is that we all rely on a stochastic optimization, right? And as my friend and colleague Léon Boutou says, is that the sort of noise that you add, that this algorithm adds into the training objective is akin to the kind of mismatch I described before, right? Between the empirical laws and the population laws. And the other one that is a bit more maybe perhaps controversial, and there was this recent paper by a student Xiwan Zhang from MIT and other researcher colleagues at Brain, is that for all we know about regularization strategies, the one that seems to work the best in practice is just to forget about this regularization and just try to make the model larger than you should think about it. And so, and this in a sense is it might make rise to a lot of interesting questions, but in particular, the thing that we will be talking about today, and is like relation to the class today, is that it really puts into this picture that by making a model large, you are basically placing yourself in an optimization problem in a sufficiently larger space, and in a sense, one question that we'll address is how this overparameterization, so to what extent making the model larger is going to make things easier, right? Either in terms of making maybe the optimization problem simpler. Okay, and so we are gonna, in a sense, we are not gonna try to solve the whole thing. We are just gonna concentrate in basically the influence of how the size of the model is gonna influence the landscape, like the optimization problem that we face. And we are gonna do this by first focusing on very simple, what we call topological properties of the landscape. So basically we look at these functions in high dimensions, and we're gonna try to study some of their topological properties. And we are also gonna not only study topological properties, but discuss and present an algorithm that is going to try to do a little bit more, that will also try to basically tell us something about the geometry of these landscapes. Okay, and so so what we are going to cover is basically these two things that I described, and then I will end the lecture with another trend, another topic that I think it's maybe might be interesting for this audience, that tries to connect the first two things with basically like a very broadly a high-level notion of statistical inference, and some existence, or how can these ideas be used or be connected with some notion of phase transition. And we will describe a little bit later what I mean by that. Okay, so this question about understanding and studying the loss surface has, as you might imagine, as you might be aware, has been recently capturing the attention and the interest of many groups in the sphere, like in the ecosystem of deep learning. Some of those works that were maybe the ones that had the merit of bringing this problem into attention were some works that try to borrow models from statistical physics, like a spherical spin glass, and try to present it as a candidate for understanding what's going on in deep learning, right? And so so these are interesting analogies, but many of the problems that we see here is that by an analogy, there's always something that you lose, right? There's some assumptions or some simplifications that in a sense give us some understanding, but there's a lot of very, very strong assumptions that make the analysis maybe less applicable to real networks. And then there are some work that I want to mention here that also try to basically ask questions about the landscape of problems that are, despite not being problems that involve deep networks, they involve objects that have some of the properties. For example, when you think about a tensor factorization, a tensor decomposition, you have some of the non-convexity that appears, and this works mostly by Anima Anandukar, and then there's the works from Shashua and his group. They're very interesting. And then recent works by also René Vidal and his group that I recommend that you check. Then a bit more related to what we are going to discuss, there's works by Ohad Shamir at the Weizmann, where it's one of the first works that really tackled or were kind of setting up the question of what happens when with the loss surface as you add, basically as you make the size of the network larger and larger. And then, so these are also works that basically focus on the two-layer problem and again the overparameterized regime. And again, more related, I think you had a lecture last week, I think, or 2 weeks ago, where Jeffrey told you about yet another tool, another angle where you can study and say things about the loss surface. In that case, using basically doing the Hessian analysis. All right. So this might sound like a very simple and I'm sorry that this is like just obvious to you, right? But just to convince the audience, historically we have this vision that the convexity isn't a necessary tool so that things can go well. Clearly that's not true, right? That you can actually perfectly define a broad class of functions that are non-convex, but in such a way that gradient descent is still an algorithm that is proper, right? That in a sense is guaranteed to converge and to find solutions that correspond to the local optimum. And these, for example, the class of quasi-convex functions is one example of that. But another instance that it might be a bit more related to deep networks is that in particular, I can take a function that I can optimize, and if I can, for example, guarantee or exhibit such a property, right? A function that has some symmetries is a function where I could perfectly optimize it to the global optimum, but it's certainly not convex. if ever the group that is acting on this function, for example, is discrete, right? I mean, potentially I can have several copies of the loss surface, right, that don't break the ability to optimize it, okay? And this, I mean, the motivation for this is, of course, that in many of the models that we will be discussing, that property, you can imagine that it's always present, right? That if you take a deep network, like more than one layer, you can do permutations on the, on the hidden layer. You can permute the rows of the first layer and then do the equivalent permutation for the columns of the second, and you get exactly the same model, right? Okay, so how are we going to analyze this thing? So the first is that we will look at these energies, these loss functions, and we are going to basically use a representation in terms of their sub-level sets, right? So basically, just think it as a, as a function where basically the object that you care about now is going to be the set of parameters whose where the loss is upper bounded by some energy level u, right? And so a first notion that we will try to study has to do with, and actually I apologize for the contrast, but I don't know if you see it here well. Yeah, I don't see it. Well, I mean, you should be seeing here like a binary image, right? And so, so that corresponds to this set. And so one of the things that we consider is like a very simple topological property. So in particular, we ask the question: are these sublevel sets connected as a function of the energy level or not? And even more, even more direct, one of the things that in particular, the question that we will ask is to what extent the level sets are connected. So in other words, can you have only one connected component for every energy value? Okay? So why is this an interesting question? And why do we care about this property? Is that obviously it provides a very strong sufficient condition for the function to have no poor local minima, right? Because if you can connect, if all the level sets are connected, it means that you can always go from one energy level to the lower one without having to increase the energy, right? So basically, it prevents the existence of local minima that are not global, okay? And of course, as I said, I mean, this property is far stronger than this property is sufficient, right? It's not at all necessary, to the extent that it's very completely easy, as I said, to find examples where you have level sets that are not connected, but still no poor local minima. Okay. And so with this setup and definitions, we can maybe start by studying and seeing what happens in the case where you have a deep, like a linear, like a neural network, where by some, you just make this exercise where you forget about the nonlinearities, right? You just assume that they are not there. Okay? And so this is a I would say, like a multilinear regression problem that includes, or that is connected with maybe other problems that you might be familiar. For example, like a dictionary learning can be connected with this, or matrix factorization is a problem where we basically have to solve these sort of multilinear regressions. And so what do we know about this problem? So this is a function that is, in general, as I said here, as I described here very simply, is a non-convex and non-concave. But it turns out that some authors, like Kawaguchi from MIT, and then like even like Teng Yuma, who is, I think, going to be faculty here next year. So he also did some work on this problem, where by assuming very little about the data distribution, for example, the fact that the covariance is simple, like no multiplicity, in that case, we can show that even though this function is non-convex and non-concave, it has no poor local minima, right? So the way this thing works is that you do basically a Hessian analysis, right? So the main property here is that whenever you have a critical point, if you look at the Hessian, right, what you would like to have is that the Hessian has at least an eigenvalue that is strictly negative, right? So that gradient descent doesn't get stuck. All right, and so what can we say about these in terms of our properties like topology and geometry? So the first thing we can say is that not only this function has no poor local minima, but as soon as you add a little bit of redundancy, so here what this means is that if I make the size of the hidden layers just slightly above the dimensions of the problem, right? then I can have the level sets are completely connected, right? So in other words, this picture that I described about, a function that is symmetric, having isolated minima, this in a sense is completely wiped out by the effect that you are making the model sufficiently large. And this is actually true also if you allow for a little bit of regularization, right? So here in the case where you had sort of a ridge regression, or what they call here weight decay, you also have this property. But this, in a sense, is an artifact of the fact that the nonlinearities are not there, right? In the sense that, sorry, what happened here? Okay, sorry, my keynote crashed. Okay, sorry about that. Okay, we are here. Yeah, here. Okay. And so this is a property that is completely universal, so it doesn't depend on the distribution, right? It works for the population loss, for the empirical loss, no assumptions on the data distribution. But as soon as I have a nonlinearity in the model, right, it's actually very easy to show that there's always you can always play the adversarial game, right? So if you give the architecture, right, we can always construct the distribution for which this result is false, right? So in other words, that in the case where we have a nonlinearities, this is not satisfying, right? And so just before we proceed, I mean, in a sense, proving this result, right, is really very simple, right? So I just want to give you just an idea of why this thing is true. And this thing is not working again. Okay. Okay, so I might need some help because. Okay. Now it's working?
Yeah.
Okay, good. Okay, so the way this thing works is that you are in this business of basically what you have to show for this result is that if you give me two models that are parameterized by this set of parameters theta A and theta B, you assume that they have the same loss, right? They have the same error. So what we have to do here is to construct a path in this parameter space, right, gamma t, such that we can go from this point, this model to this model, in such a way that the energy along this path doesn't go above basically stays in the level set, right? So that's what you have to show if you want to prove connectedness. So the way it works is that, and in a sense, it's going to be, we are going to understand why this thing comes, why this thing is general and connects to other areas later, is that this result, if you have only one layer, is obvious, right? If you only had like a least squares problem, you can always connect two models that have the same error with the path because the problem is convex, right? So a line would be sufficient to prove this result, right? It's completely trivial in that sense. So the way this thing works is that we are going to basically prove the result as we increase the number of layers by basically lifting the problem by basically assuming that we were in this linear regression problem and then having to factorize the corresponding path, right? So basically, you go into the regime where the loss is convex, basically by changing reparametrizing the parameters of the model, and then once you have this connectedness, you try to factorize the path in terms of the original parameters. And at the end, the reason why we need, arguing in terms of the number of parameters is basically resolved, or it depends on this property that if you look at basically the space of invertible matrices, right, the space of like the general linear group, it's a group that has two connected components, right? The matrices that have positive determinant and the matrices that have negative determinant, right? And so if you want to have a path that connects from one to the other, if you don't add a little bit, if you don't add this extra dimension, right, that we have here, you cannot connect from one to the other, right? But as soon as you add just one dimension, then you can basically jump from one connected component to the other. Okay, that's the simple idea in a nutshell. Okay, so as I said, this is a result that is like much stronger than the original question, right? Why does this loss surface have a poor local minima or not? Yes.
Problem
Exactly. So this is a loss surface that is symmetric, right? You can permute the weight, etc. Oh, yes. So the question was, here we are not exposed to the problem of the symmetries, right? The group symmetries, in a sense, don't make the level sets disconnected. And this is because we are paying a price, right? We are making the model just slightly, we are adding just enough neurons such that we can basically wipe out the discrete symmetry group. Okay? But it's a very relevant question because it connects with my next slide, is that so basically this question, right? How much are we paying? How much extra redundancy are we paying to allow, to prove a result that is stronger than what we had to do originally? And so this is some extensions that we are doing together with our PhD student Luca Venturi and my colleague Afonso Bandeira. And so one of the ways where you can basically get around risk and try to remove this redundancy is to essentially use the same, do the same thing, but instead of working on the natural parameter space, you work on the quotient group, right? Basically, you all set of parameters, you create this equivalence relationship that if the two set of parameters, they are equivalent, right? If you can relate them from an element from the general linear group, right? In other words, you think about you look at this problem, at the topology, in what's called the Grassmannian, right? It's the space of subspaces. Yes?
That I must be missing. Does it mean the orthogonal group?
In that case, no. Even the linear group, right? Like the invertible linear group.
It just means that W and W squared all have the same rank.
Yes, it means that basically they basically generate the same subspace. So basically, what you yes. Okay, and so with this, basically what we show is that basically we kind of relate to go back to the question of just poor local minima, and this is a result that now doesn't have any assumption, right? Basically, you don't need the covariance to be like full rank, etc. Basically, by applying the same result. Okay, but in a sense, this is again something that is only partially interesting because there's no nonlinearity at this point. So, as I said, I mean our objective is really to go to the nonlinear case, right? So between the linear and the half rectification, we can maybe make a stop in the middle. There is a nonlinearity that is a kind of a gentle nonlinearity, right? Which is basically looking at the square. Okay. So it's not a nonlinearity that is being used and popular in the community, but in a sense it's informative because it tells us something about the underlying, basically the underlying, in a sense, the way these things are proven, right? And so here, what we do is like a trick that is, of course, not new, and many people here from this audience have used it, and mastered it in the past. Is that this idea that you can basically linearize this nonlinearity by lifting the problem, right? Basically, by rather than replacing the input by the outer product, and by replacing your parameter by basically also a kind of an outer product of your matrices, right? And so once you express the nonlinearity like this, we have an automatic extension of the previous result that says that in the case where you have this nonlinearity, again, if the size of your hidden layer is, in that case, larger than the dimension of now your new input, right, then the landscape of this problem is simple, right? There's only one connected component. So again, this is something that it should not be very surprising, right? Because what we are saying is that we are giving the system enough liberty, enough redundancy, so that basically you can jump from one local minima to the other, right? And so here there's this funny factor that I think it's just an artifact of the proof, but the idea is the. And of course, this result you can just apply it repeatedly to different layers, and you get this ugly expression that says that if you keep repeating the argument and every time you keep making, basically you replace this thing, now you will take another square, right? So you will take the outer product of the outer product, right? And so if you keep doing that, you have a very automatic result that says that you can have no poor local minima for a k-layer network. All right. And so so here one of the things that we are currently wondering is whether if you basically do the same thing as we did before, going from the original problem to the problem on the Grassmannian, if you can actually gain, like reduce this rate, right? So right now we are only able to replace the constant, so we are not able to replace this n squared, right? We just yeah. So it's currently, I don't know. I don't know whether it's true or not. Okay, so now with this we can do the full thing and basically now try to say something about the case that is really interesting us, right? The case where you have this half rectification. And so in that case, we are going to again simplify things a little bit. So we are just going to work on the case where you have two layers, and we are going to basically regularize the problem by adding a L1 penalty on the second layer, and by projecting the first layer to the sphere, which is because this nonlinearity is homogeneous, doesn't lose any generality. Okay, so in that case, what we have is not the argument that the level sets are connected, but we get something that recovers some form of asymptotic connectedness, I would say, right? So in the sense that if I have two models, okay, that have the same loss, I can connect them with a path that might have to go above the energy, but the amount of which I have to pay, so the amount by which I need to increase the energy, is a quantity that vanishes as the size of the hidden layer increases. Okay? So here, for those of you who are familiar with basically non-parametrics, you will see something pretty ugly, right? What is ugly here? The rate is basically as bad as it can be, right? The dimensionality of the data appears not in the right place, right? But in a sense, this is basically we are cursed by the dimensionality, right? If we want to make the error twice as small, right, we need to basically increase the size of the layer by exponentially, something that depends exponentially on the dimension, right? But in a sense, this is it's maybe a consequence of the fact that the nonlinearity that we are using is essentially counting half spaces in dimension n, right? So basically, the way this thing works is that if I'm in dimension n, right? If I have enough of these if I have enough of these neurons, right? I will be essentially I will be covering the unit sphere of dimension n with half spaces, right? The things that basically detect half spaces. So, if I have an exponential number of them, I will be able to basically cover the unit. I will be able to cover the unit ball. So this is what this this result explains, right? So basically, the idea here is that it's just very it's fundamentally hard to relate one nonlinearity like the fact that we use values is really making us pay this course of dimensionality. And of course, one of the open questions, one of the things that we are wondering, and that might be interesting, is to see if we can recover some kind of polynomial rate by making the nonlinearity a bit more gentle, right? The fact that we are not just measuring half spaces, but something that is a bit more smooth. Okay, and so why I think that this is an interesting question is that this relates or connects with something that for people who are not just doing machine learning in the last 5 years might be very familiar, right? This idea of kernels, right? Is that the technique that we are using and the way we are addressing this problem is by all the time trying to think about the network as basically we are trying to linearize the network, right? We are trying to basically separate the role of parameters and data in a way that they basically live in that basically you can think about learning as like solving a least squares problem, right? And this is again something that was it has a long history in machine learning through this theory of reproducing kernel Hilbert spaces. Okay, so just to illustrate this thing, we can look at these models, right, in two different ways, right? Either we look them in what I call these network parameters, right, where things are all like entangled in these layers, and then the paths that maybe I have to go from A to B are going to be very complicated. Or I can lift the problem such that basically I can exhibit this what I call these canonical parameters, right? And then in that case, you can connect models by just following the linear path, right? So basically, we are working on this thing, and in a sense, this vision automatically generalizes the setup with a quadratic nonlinearity, in the sense that if I can still, as long as I can basically think about the canonical parameters in a finite dimensional setting, like in the case of square, it was lifting from n to n square, right? So if you replace n square by something that is finite dimensional, then it's automatic to see that if you overparameterize by this amount, then this thing has no poor local minima. And so, of course, the thing is that if rho is a value, right, this thing is not true, right? I mean, a value cannot be embedded in a finite dimensional space. Okay, and so just for reference, there's a lot of, I say, recent activity on trying to connect convolutional neural networks with reproducing kernel hero spaces. You had here in this class Zaid, right, who talked about basically a predecessor from this work from Julien Meral. He has like a new paper on developing these kernels. And then I think there's also work from this school, right? Percy Liang has a very nice paper on convexified neural networks that really makes this connection a bit more precise. Okay, and this is something that I forgot to remove from the thing. Sorry. Okay, and so okay, so now I try to give this, a set of like picture on the connectedness of the level sets. One of the things that we were interested in this work is also to try to ground, or like to have something that could be applied, could be measured on real networks and real problems, right? And so one of the, the conditions that we studied so far are, in a sense, very weak, right? I mean, saying that there's no poor local minima does not really inform me whether my stochastic gradient descent or my descent algorithm is going to work well in practice or not, right? There are many things that could happen. There are many bad things that could happen, right? So in particular, by simplifying and sketching things a lot, we could wonder whether we are in a regime where the level sets look like nice looking convex bodies, or do they look like very complicated, high dimensional tentacles, right? Because in that case, probably you would say that it's very easy. It's easier to navigate from one level set to the other. Like it's easier for the gradient descent to behave in this world than in this world, right? Where you might have to go from here to here by just following the gradient, right? So one of the things. So how can we have a diagnostic tool that will tell that whether in practice in deep learning we are more on this world or in this world? So one of the things that we try to do is that we try to estimate geodesics, right? So basically the way we do it is that we sample 2 points independently from the boundary, and then what we try to do is to try to connect them, right? To try to find a path, and we try to find the shortest possible path that stays in the level set. And basically the length of this path can give us like a very crude geometrical information on how curvy they are, right? So if they were convex, we would have things that have basically a geodesic normalized length that is 1, right? Basically the length of the path divided by the linear, by the Euclidean distance between theta A and theta B would be 1. And so how do we implement this algorithm? How do we have an algorithm that does this? Well, we do something actually pretty simple, is that we use a dynamic programming approach, right? So I give you 2 parameters that are in the same level set. We are going to try to find a third model, right? That tries to stay as close as possible from the middle point, right, while staying in the level set, right? So we solve this optimization problem, and so once we have found it, we just repeat the thing, right? Basically, we fix this point, and then we try to find another point. Okay, so and we just repeat the algorithm until we reach a certain, of course, a certain critical distance between the models. Okay, any questions on how this thing would work in practice? Okay, so now we have a very simple tool that can tell us, maybe can inform us about what's going on in practice, right, in real models. And so, so for example, you can try it on, you can just try to amuse yourself, just kind of like a unit test if you want. You can make, of course, the regression problem as complicated as you want, right? And indeed, it seems that this corresponds to what you would expect, right? Like this is a classical problem that you can even visualize, right? It's like you look at the loss surface, that if you look at it from a level set that is sufficiently high, everything looks like a convex body, right? Everything looks like a circle, so you get a normalized length that is very small, right? And as soon as you hit some barrier, you start to see funny things. So what is interesting is that if you look at the unit test in deep learning, which is MNIST, you see that the picture is actually not too different, right? I mean, the level sets here, they are almost convex, right? The curviness, the amount of curviness that you add is very small relative to the length, to the distance of these two things, right? And so here you can associate this with saying that, MNIST is you can quantify how easy it is, right? By maybe looking at this thing. Yes?
So I don't understand, is 1.08 a big number, a small number? I mean, the difference of 0.8.
Yeah, I mean, maybe, so what you can say is now compare these numbers with, let's say, CIFAR, right? Now you can look at two different data sets with two different architectures, and basically, I mean, it's really a diagnostic tool that already what we see in practice is that a priori, there's no reason why two models should be connected, right? Be in the same levels, like the level set should be connected. So the first observation that we have here is that we are always able to connect two models, right? So in other words, I mean, this of course is not implying that we can prove that the level sets are connected, because it's to the extent that we can sample points. So basically, showing that you have 2 points that are disconnected means that it's disconnected, but showing that you can connect doesn't mean that things are connected. Question? Okay.
But also, here, for example, for CIFAR and this, the distribution of the data is different.
Distribution of the data is different, yes. The input dimensions are a bit different, right?
So how do you compare these two numbers?
So sorry? Oh, so yeah. So of course, these numbers, you should think them as, this is just the relative distance, right? So of course, it's something that there might still be a dependency on the dimensionality of the parameters, basically the size of the data set, etc. But in a sense, what we try to see is that for us, I mean, we were not expecting to have a behavior that is in a sense closer to what you'd imagine like a low-dimensional problem, right? Where the amount by which you need to curve things is not too high, right? And even like problems that involve basically character prediction, like this is like for text modeling, right? Okay. So what I try to say here is that, well, I mean, there are things that we expected to find, right? For example, the fact that the level sets become more irregular as the energy decreases. This is somehow a phenomena that one could expect. But the things that are maybe less that we are not expecting is that in practice we find that there's still like a gap between what our theory is able to explain and what's happening in practice, right? Because it could perfectly happen that there's no reason why two models that you train independently should be in the same connected component of the level set, right? And so this is something that, of course, we need to do extra theoretical effort to be able to understand them. And so there's a number of questions that I think that could be interesting, is maybe to push this idea of how can we generalize these questions of landscapes by using the reproducing kernel Hilbert space. And again, one thing that we didn't cover at all, and we are completely still in the dark, is how does this play, or how does this relate to the question of generalization, right? So basically, this was just a pure analysis of these loss surfaces, right? And we were not, we didn't study the influence of the stochastic optimization, and we didn't study the influence of basically the fact that we are optimizing a function and we are testing on a different function, right? And so one of the things that we are of course interested is in understanding this, whether this thing can also explain generalization. Okay, so now I will basically move to a second part of the talk, where we are now try to focus on a more specific class of problems. Yes.
Mind if we just take some questions?
Oh, sure. Yes.
Before changing parts of the talk, the students had a number of questions that they posted us on the course website. Stanford has a discussion section, so I just thought we'd go over a few of those before leaving this part.
Sure.
So Yifan Wang and Prayaksha Sharma question the issue about there's some language in some of the papers for the reading, all minima are good minima.
Uh-huh.
And could you just explain or amplify a little bit on that?
So yeah, I'm assuming that this might mean different things, and so I have two possible interpretations. One is a purely like non-learning interpretation, where what does it mean? It means that a given function, I can look at all the critical points, and I can look at the critical points that are local minima, and then maybe meaning that all minima are good minima is equivalent or is related to this notion that all the local minima are in the same energy level, right? So all the local minima are global. The other interpretation is in terms of generalization, right? So that to what extent the minimizers of the empirical laws are going to generalize equally on the test set. And this is as far as I know, it's completely open, right? We have very little understanding of this second property.
Thank you. Fan Min Nguyen had multiple questions, but one of those seems relevant. So he mentions a recent paper by Din, Pascanu, Bengio, and Bengio that points out one can reparameterize a network so that flat minima are turned into sharp minima, yet this doesn't affect generalization. And he's wondering if there's anything in your work that reflects on that paper.
Yeah, so I haven't read the paper in detail, so I'm not very qualified to comment. But I have to say, on this question about the flat versus narrow, I think that right now it's honest to say that we don't know. I mean, there's some contradictory papers, right? There's some arguments towards one solution, some arguments, as you say, this one, that seem to offer like a negative counterexample. So yeah, I think that it's fair to say that we don't really know. And definitely what I described here could be related, but I haven't made the sort of the precise connection. So but it's a very good question. It's something that is definitely worth investigating further.
The students posted many more questions, but I think we'll try to do them after the rest of the time.
Perfect. Thank you. Okay, so now I will just try to briefly connect some of these ideas to another aspect of our work. And so just by like very broadly and like high level thing is that we kind of discussed this notion of learnable hardness, okay, whatever it means. So for me, this is like a very qualitative way to say that there are some problems that are easy to learn, in which the gradient, the loss surface is sufficiently simple that we can, reach good values of basically of the loss, and there are some problems for which this thing is harder, right? And so as in more general domains, in statistics and computer science, we also have other notions of hardness that a priori have nothing to do with this learnability hardness, right? And so in particular, we can talk about problems that are statistically hard, right? And we'll give more precise details later, or problems that are computationally hard, right? And so these ideas from statistics and theoretical computer science. And so one question is, okay, how can are these two things completely independent, or can we somehow build a program where we can kind of combine these notions of hardness, right? And so for this, it might be a good place to start to consider neural networks, fit them, or consider or like try to apply them on let's say classical statistical inference, statistical inference. Okay, and this is again motivated by several fields. So in particular, you could also motivate this question from the computational trade-offs, right? So you might want to see if neural networks can be a good tool to find a good trade-off between statistical accuracy and complexity, right? And so I will briefly discuss like a very famous, or like a canonical setup that is, I'm sure, very well known here in this house, right? That is the sparse coding, right, or the sparse inference. And so I don't have to basically tell you what this is. This is just solving this convex problem. And so this is a problem that is convex, right, as you know, but it's not strongly convex. And so how is this problem typically approached, right? What is the algorithmic solution to that? Again, many different ways to attack it, right? In particular, one that we will use as a vehicle is this idea of splitting, right, the proximal splitting. And so, again, I will just go briefly with that, is that if you just follow this rule, right, basically you define this iterative algorithm that essentially takes the current estimate and applies basically this, something that looks like the kernel or the kernel matrix of the dictionary, and you combine it with the soft thresholding. Then it's this, again, very classical results that tell you that this algorithm is going to converge to the solution, right? It's going to converge, and we know things about the rate in which it converges. Okay? And again, by no means this is the only way to solve it, but it's one that is going to come handy for us. Okay, so again, sorry about that. Okay. Sorry. Okay. And so, yeah. So formally, you can look at this algorithm as if you like to write boxes, right? You can write every linear step with a box and every nonlinear step with a box of different color, and you can look at the algorithm at this proximal splitting as this infinitely large like neural network, if you want, right? But the weights of this neural network are completely determined by the algorithm, right? And so what Carol Gregor and Jan LeCun proposed some years ago is to say, well, in a sense, a very naive, a very simple question, right? What if we only care about, like a finite algorithm that will run in m steps in, finite computational time? What is the best way to organize these computations, right, to be as good as possible in terms of solving the problem, right? And so this is something that was coined as this lista. And so in practice, it worked very well. And so the reasons why this thing worked well, in a sense, are not very mysterious, right? And so for this, you can think about you can analyze them and reason about this adaptation by basically looking at the geometry of the optimization problem, right? And so the principle of these splitting algorithms, it's actually very simple, is that they involve a L2 norm which is separable, right? It's like something that is, it has a lot of symmetries with respect to rotations, and it has a term that is the L1 norm that is only separable, it's only easy to think about in a very specific coordinate system, right? Which is the canonical coordinate system. Okay, and so what it means is that you can write this norm in the canonical system as it can separate, right? And so by exploiting the convexity of the problem, you can you can replace your problem with a surrogate, right? That again is also like separable, right? It's a Taylor approximation where this is separable because you construct this second order approximation to be basically a function where this quadratic form is typically diagonal, right? So basically it's separable. Okay, so now you can, rather than optimizing the step, right? You optimize basically the upper bound, the quadratic approximation at every point, right? And by following this, you basically end up with this proximal splitting, right? So there's this very simple remark that now, before applying this proximal operator, you can rotate the space, right? Now you can basically consider like a unitary matrix, right? Before applying the proximal step, and then basically consider a upper bound where basically it's expressed in terms not of the original canonical system, but in terms of a rotated version of the canonical system. Okay? And so the observation, and very simple thing, is that this is still a proximal operator, like optimizing this thing analytically can still be done explicitly, right? It's basically it has an explicit solution because it's just essentially a change of variables, right? But of course, it has this question of, okay, how can we choose this rotation, right? And so the original splitting algorithm does not consider any rotation, right? You just use the identity. So here the question is, how can you choose the rotation, and what is the impact of rotating? So as I said, I really don't know what's going on, but.
Can you clarify? Are you rotating the L2 loss squared, like you're
rotating, yeah, the whole thing. So.
Like graphically, you usually have this ball and you have this diamond. So
Yes.
you're rotating the
So you are basically you are rotating the diamond, and then you are redefining. I mean, you are free to choose the S, like the upper bound, as you want, right? So yeah. So let me just continue. So the way, I mean, if you start to rotate the space, the L1 ball seems to be a very bad idea to rotate the L1 ball, right? Because something that is aligned with the axis now is going to be completely off axis, right? And it is true. I mean, you lose something, but what do you gain on the other hand, right? So the thing is that in this algorithm, you have on the one hand an object that is aligned with the canonical axis, and on the other hand, you have basically the gram matrix of the dictionary that might be aligned in a completely different direction, right? So in a sense, you have two sources of error, right? It's durability. So how the L1, basically how this rotation is going to perturb the L1 ball, and on the other hand, how the rotation is going to diagonalize your gram matrix. Okay, and so these two sources of error, it's easy to see that together they give you a guarantee, a control on basically how much improvement do you do applying every proximal step, right? The amount by which you can reduce the error in every proximal step depends on basically how well you are able to balance these two error terms. Okay, so ideally, you would like to find a factorization, like a rotation, where the residual is small, meaning that this thing is not too far from diagonalizing the gram matrix, but this thing is not too large, so you don't want to go very far from the canonical axis. So those of you who are familiar, let's say, with sparse PCA, you can start to see the connection, right? You want to basically take a gram matrix and find a diagonalization of the gram matrix that is not too far, that is sparse, right? Where the eigenvectors are not too far from the canonical axis, right? And so it's, in a sense, it's when you simplify the analysis and you just make everything generic, like for example Gaussian, right? It's very easy to see that if you want to optimize the trade-off between these two terms, essentially as soon as there's this simple condition that is verified, and we'll expand on this in a bit, the solution, the optimum, is never to choose the identity, right? In other words, it's essentially always the case that you can do better than ISTA, right? By finding the appropriate rotation of the space. And so what is interesting is that basically what is interesting here is that we see that our ability to satisfy this question depends on how far we are from the optimum, right? So if we are getting very close from the solution, it's less interesting to adapt, right? It's less interesting to find the rotation, which is the thing that we observe in practice, right? That these algorithms that accelerate, they work very well at the first iterations, but then at some point, it's less interesting. And then in a sense, as the dimensionality of the problem increases, it becomes easier to do, right? So again, for those of you who are familiar, this is related to sparse PCA. And I'm not going to show you numerical examples, but this is an idea, like it's just a very simple analysis that really, so of course now the network is not solving this problem, right? The network is just choosing these rotations in a completely supervised fashion, right? But in a sense, this creates the conditions for this thing to work well. And then I will just finish this lecture in 4 or 5 more slides, where we can jump from the problem of basically using a network to do sparse coding, which in a sense is something that we all know how to do and we have done all very often, to maybe a statistical inference problem that are a bit more challenging, I would say. Things that where we can really touch the notion of statistical hardness, right? And one example that we considered, and this is joint work with Alicia Lee from UC Berkeley, is again the well-known problem of community detection, right? And so here the goal of the game is that you observe a community of people, like an ensemble of people, and you only observe basically the friendship relationships, right? And you need to infer the communities. And so this is you can basically you can look at this problem by basically finding what is the assignment of probability of the assignment of communities that maximizes a quadratic form. And so there's one line of work where you try to find reasonable estimates by relaxing this problem, right? This problem is over a binary cube, and then you can relax it using maybe like a semi-definite program. And you can also think it from the perspective of a posterior inference on a graphical model, right? And using algorithms that relate to message passing of loopy belief propagation. And so I'm not going to go a lot of details, but it turns out that when you study this problem on a very simple statistical setting, the stochastic block model, then we can understand well when is this algorithm, when is this like inverse problem where I observe this adjacency and I need to infer this community, when is this problem statistically feasible, right? So in other words, which conditions of signal and noise, which here correspond to this probability that I will connect if I'm friends and the probability that I will connect if I'm not friends, there's this remarkable understanding of this problem that really tells me that this problem is statistically feasible only when the signal to noise ratio is above a certain threshold, right? That is called the Kertzon-Stegen threshold. And so, and it says that there are two algorithms in the case of two communities that achieve this threshold that really correspond to the two things that they describe, right? Like basically using a spectral algorithm on an appropriate operator on the graph is able to achieve this threshold, and then the loopy belief propagation. So why am I talking about this problem? Is that now we can look at what would the spectral algorithm look like, right? So the way I describe it is that you can look at these estimators that have this like generic form, right? You take a graph, you consider a certain operator on this graph, for example, the graph Laplacian, and then you basically look at the spectrum of this operator, and you extract a very specific eigenvector, right? The one that is like this corresponds to the second smallest eigenvalue. And then in the case of a binary, in the binary case, you just take the sign, and this defines an estimator. And so this, following basically the story of a sparse coding, you can unroll it, right? You can look at this algorithm as basically applying a collection, an iteration of projected power iterations. And so in that case, you can also consider what is the neural network equivalent of this, right? Can we unroll this algorithm and try to see to what extent this algorithm is able to match, maybe in that case, to match this information theoretical threshold. And so in that case, the right language, the right neural network, is a neural network that lives on graphs, right? That basically it's the same thing as a convolutional neural network, but instead of having local derivatives as generating the convolutions, you have basically a very in a sense a low pass filter on the graph, that is the adjacency, and a high pass filter on the graph, that is the Laplacian, right? And you just learn linear combinations of these things, you cascade, and you can train the parameters of the model exactly as if you were solving a classification problem. And it turns out that that this algorithm works very well. I mean, same observation, as with the lister, right? That you unroll this algorithm, and it, in a sense, it matches the performance. It reaches what we call this, at least empirically, the information theoretical threshold. And the advantage, of course, is that with this, you are not married to the generative model of the. You can replace the data coming from the stochastic block model with real data, and in this respect, we have like nice improvements. So how does this connect with this idea of this general concept of phase transitions, right? And so in that case that I described, as I told you, there's basically there are two regimes, right? In the case where we have two communities, right? What is known is that the information theoretical threshold matches the computational threshold, which means that we have polynomial time algorithms that are as good as they can possibly be, right? And this is the the limit in which they start to work well. And so, just as a kind of a research question, the thing that we are trying to study is to what extent now this phenomena can be associated with something that changes or some effect in the landscape of these models, right? Because what we have seen is that we can maybe attack this question by associating a statistical inference problem with a learning problem, right? Where we try to learn a network that tries to solve this problem. And so here we don't really know, what we're going to observe is a bit of anything, but perhaps more interestingly are problems in like more complicated problems, for example, that arise when you go from 2 communities to 4 communities, where in fact it's not known, right? We know that there's a information theoretical threshold that is somewhere here, and we know that there's a threshold above which we know the algorithms that work well, and we don't know what's going on here, right? We don't know whether there's an algorithm that can be efficient or not. But now we can use our kind of neural network hammer, right? And say, well, why don't we just train the network? I mean, the network is trained exactly the same way, whether I'm feeding not a lot of noise or a lot of noise, right? For the purposes of the supervised learning problem, formally nothing changes, right? And so the question is, do we observe a kind of a phase transition in the landscape, right? That it's going to maybe make the landscape look different when the problem can be solved, or are we going to observe something here? And more generally, can we use this framework of learnability thresholds to say something about the statistical thresholds? And I think with that I'm going to just end. And so if there are some more questions, we can discuss them here. Yeah.
So there were some questions that I written down. Casey Chu is asking about the difference between the level sets of the training versus the test loss and how they are going to differ.
Yeah, that's a good question. So in our analysis, we only use basically the covariance of the distribution. So in other words, our results apply either for the empirical loss and the population loss. But of course, this doesn't mean that these energy landscapes are going to be, behaving the same way. So I know that there's some work also where people try to again relate the two losses using Langevin dynamics. So I know that there's some recent work actually from people, I think a postdoc here at Stanford, that address this question. It's very interesting, and besides the fact that when the number of samples is very small, then you can simplify a lot this analysis. For the rest, it's not something I can say anything. Yeah.
So many students had these questions like about your paper topology and geometry of half rectified. So they're asking whether, so in the paper you assume 2 layers, and how does basically your result, how does your result change if you go to like deeper networks and more layers?
Yeah, I believe that the result would still hold a given amount, sufficient amount of redundancy, but we haven't done the mathematical analysis, so this is again something open. Yeah.
And one more question that I have is, some people are asking about the practical application of your results, and they're asking whether your results that you presented to us today would shed light on how to design the architectures of these networks.
It's a good question. I don't have a direct answer, but for example, one of the things that we want to use to make it a bit even more connect them even more to the practical implications is to relate them to this paper by Xiu and Yang, right, where they use these noisy labels. Okay, so there what they observe is that if you let's say randomize the labels, you can you can still make the training error go to 0. And so this raises questions about their generalization. But here we can now use this analysis of the loss surface to see, okay, you can solve the training problem with the right labels or with the noisy labels. In both cases, the network succeeds. But is it going to have a harder time in the sense of, are these numbers that I showed going to reflect the fact that in one case you were solving the wrong problem, whereas in the former you get something regularity. So in other words, you can exploit the regularity of the level sets as a tool to control generalization. But again, it doesn't have a direct practical implication, but it can be used, it can be plugged into the machinery to basically control generalization.
Some other students, I think Michael Kelly, Shi Dong, and Kenneth Tai had questions of the following nature. In your paper, Topology and Geometry of Half-Rectified Network Optimization, you mentioned you've got a mix of L2 and L1 norm constraints. Can you explain the intuition behind your belief that more general regularization schemes will yield similar results to those demonstrated in the paper?
Yeah, so the way these norms were chosen, it's more it's more like an artifact of the proof, right? So the proof is based on this idea that you can connect, you can move from one model to the other, right? And so having a L1 on the second layer is useful because it means that it's not hard to basically set to zero some of the weights, right? It's something that promotes using very sparsely the hidden layer. So in that respect, and actually, and in a sense, this use of sparsity is not new, right? That there are many other instances of, like, for example, Sanjeev Arora's paper and Teng Yu Ma's. They also use this idea that sparsity in the activations is a tool that can give you a lot of mileage. Whether this thing can work with more general regularization, I believe so, right? I mean, in practice, people are using different sorts of regularization, and the empirical results seem to be that we obtain about connectedness seem to hold. So maybe my answer would be that yeah, it might be possible. I don't know how to prove it for other norms.
Aurora assumes the activations are sparse. You assume that the weights are sparse, correct?
Well, but that's true.
Okay.
So yeah, that's true. It's different. Yeah.
I'm just saying.
But they also say that you can identify the network, right? So the network is characterized by the weights. So they assume sparsity on the weights, I think, but I might be wrong. Okay.
Shi Dong wondered whether you can do anything for Tanch and some of the other nowhere linear methods.
Yeah, so the program or the machinery would say, if you give me a Taylor approximation of the nonlinearity that decays sufficiently fast, so if the nonlinearity is analytical and I can think about it as a kind of a fancy polynomial with some residual that I can control, then that could be plugged into the proof techniques to obtain a bound like this. Whether this is going to be useful or it's going to be like a useful and realistic gap, I don't know. This depends. We should do a more detailed analysis. But as soon as the nonlinearity is analytic, I think that you can you can still recycle some of the tools here.
Any further questions from the audience?
I just didn't understand the neural net that you were training on the graph in the second part of the talk.
Yes.
What was the data and what was the labels and?
So we had the two settings. One was the stochastic block model, in which the input is the adjacency matrix and the targets are the labels of basically the way you construct the sample from the block model is that first you sample communities by sampling a random partition, and then once you have the partition, you sample the adjacency.
So are we assuming that we are getting multiple views of the?
No, just so basically you have, when you sample from the stochastic block model, you have the adjacency, and then you have like a latent variables that are the labels of the nodes, right? So what the network sees as the input is the adjacency, and it needs to predict the labels.
But we are observing various adjacency matrices.
Oh yeah, and then of course we sample IID. So in the loss. So here we have basically different samples from the IID samples from the SVM. So that's for the SVM, and then for the real community detection, we just replace these samples from like adjacency and ground truth labels.
So if I see a few examples coming from the same stochastic block model, is it true that the information theoretic threshold would be the same information theoretic threshold that you showed me earlier?
So this is how we reached it. Basically, we just sampled IID some examples from the block model, and we even like consider like a mixture over the parameters like P and Q, like the probabilities, and then you just show the performance in terms of the signal to noise ratio, and you get like essentially you match the performance of basically the algorithms that match the information theoretic threshold.
But is the information threshold that amount? Because I think that value is when you only observe one adjacency matrix and no labels or...
No, but the way it works is that for a given, so you give me one graph and one observation, and then the model predicts the labels. And then you, yeah.
So is there a question from the audience? We have a question.
I was wondering for the level set part, how do you actually get two sets of parameters that have the same loss?
In practice?
Are interestingly apart. Like, if you do an optimization procedure, it feels like you will get related set of parameters.
So we initialize them, so we sample them from basically independent initializations, and then we also tried like running one with batch size equal 1 and the other one with batch size equal 16. Like but you're right, and actually this is a point that we didn't address, that you could like do like adversarial initialization, right? You could say, okay, what is the worst possible initialization that I could consider? To basically you could say, okay, I have one model that initialized with that space, and then maybe you could sample from something that is, you know, I don't know, farther. Yeah, these are all interesting things that we didn't. There's a lot of things that can be explored. Yeah.
Okay, well, if there's no further question, let's thank Joan.